So our next speaker for today is UK Anandavardhanan from the Department of Mathematics at IIT Bombay. Anand did his bachelor's studies at Calicut and then his master's and PhD at the University of Hyderabad. And then he spent some time as a postdoctoral fellow in TIFR, I think somewhere in Iowa in the US also, before coming to IIT Bombay as a faculty member. He's been there for almost 20 years now. Very early on in his career, he was recognized all the science academies in India in some form as a young associate, a young scientist, and so on. In 2020, he was awarded the Shanti Swarup Bhatnagar Prize, which many of you know is one of the top science prizes in the country. Last year, he was elected a fellow of the Indian Academy of Sciences. He works, he's a mathematician, and he works in representation theory, automorphic theory. Today, he's here to give us a gentle introduction to number theory, to tell us about what are the kind of questions that exercise the minds of mathematicians.
So thank you, Professor Mahajan, for the kind introduction. And thanks to IMSC for this gentle invitation to come here. And this outreach program has been going on for many years extremely well. And I'm very happy to be here as part of this prestigious outreach program and on this prestigious venue on both counts. So thanks so much. So I have given this title, A Gentle Invitation to Number Theory. Number theory is something that all of you have heard of for sure, and it's about numbers after all, right? And numbers is something that all of us deal with on a day-to-day basis, and in school you do see some basic things, and later some of the things one might forget. So I have given this generic title, but there are so many, and in the abstract I have said that among all the areas of mathematics and in many other human endeavors, this particular one, number theory, is also known for, among various things, one particular property, which is that there are so many problems which number theorists are interested, mathematicians are interested, which are not very difficult to state. Give 5 minutes and then one can introduce nicely and then you completely understand the problem. But then often what happens is some of these problems are so easy to state, one can convey the problem precisely to people without so much background knowledge. But then solving it becomes very, very difficult, and it can take years, it can take maybe 100 years. And I'm going to focus on one problem as an example, where as you will see when I go to the slides, the problem was posed many centuries ago, and even today it's not fully solved. Okay. Whereas a problem, if you pay attention, it's not very difficult to understand what the problem is. One might ask why one is interested in these problems. As the previous speaker said, we share this world with all of them, so we should know them. These are problems that our ancestors, the human beings have naturally come up with, and therefore we should be interested. Right? It's about human curiosity. So let me start. So the problem is called the congruent number problem, some name. So the problem that we are going to discuss goes back to Persian mathematics of the mathematicians of the 10th century. So many years ago, right? Centuries ago. And just a historical introduction in whatever references that we see, two names are mentioned. I don't know much about them, but whatever I have seen, I have put in there. Al-Khazin, 900 to 971, and Al-Karaji, more or less the same period. And in an article I saw that it was Al-Khazin who formulated the problem, which has become, and many things I have deleted there, but a very favorite topic of lectures for a wider audience. Because of this thing, it has been posed long ago, and it's not fully solved. And so it gives a good opportunity to introduce why, in order to solve some basic problems, one may have to have an advanced theory, etc. So it's a common topic that people take if this kind of invitations come, and I have done the same. I have followed others' footsteps. It's called the congruent number problem. Okay. So what is called a right angle triangle in school you might have seen, one might have seen, it's a triangle where one of the angles is exactly 90 degrees. So here if you take this bottom part with this red thing, this angle is 90 degrees. So that's called a right angle triangle, right? And the problem is about right angle triangles in some sense. So there's no numbers here. I mean, numbers will come. So one could just say that, if you don't want to know what a degree is, etc., it is take a rectangle and take 1/2 of it. That's a right angle triangle. So this rectangle has given rise to, by my cutting the diagonal, 2 right angle triangles of same shape, same area, etc., right? And what is the area of this rectangle? Not the triangle, the full rectangle. One side is 3 and the other side is 4. So the area is 12. And therefore, what will be the area of this bottom triangle? 6, obvious, right? And the other half is also 6. So 2 triangles of area 6. So so once you know the length and height, let me say, the breadth and height, let me say, then you know the area. It is just half of the base length times the height length, right? And there is this famous property about such triangles. These are triangles where 1 degree is 90. It's called the Pythagoras theorem. And here I have given the years in the other order, and you know what it means. It's BC. Okay, so 570 BC to, so this is long ago, before Christ. And this is from Wikipedia. And I will not get into this. So there is this famous theorem which we see in school. Does anyone want to quickly say what it is? I don't really need it, but yeah. Yeah, maybe I am far from, yeah. What is A, B, and C?
A is one side, B is the other side, and
C is the bigger side, the hypotenuse, right? Yeah. So here are 2 quick proofs from Wikipedia that I have quoted. This much is one proof of that. Have you seen a proof also?
Yeah, you extend
Fine, good, great, yeah. This is one proof, this is another proof, but we are not getting into proofs and all that. It's right there in Wikipedia. It's a very beautiful theorem. So as he said, it just says that in this particular example, 3 is this side and 4 is that side, and that bigger side is called the hypotenuse. And if you square this and square that and compare, this is 9, that is 16, 9 plus 16 is 25, which is the square of 5. And this property is true for any triangle where one of the angles is 90 degrees. If you take the 2 small sides and take the squares and add, that will be the square of that hypotenuse, which is not all that obvious if one just looks at it, but then there's a nice proof. There are many nice proofs. Okay, so let me say something more basic. By natural number, one just means the numbers that we use to count, 1, 2, 3, 4, etc. Right? So those are the natural numbers, all of us know. And then there are these rational numbers, which are, what you call fraction. So what are fractions? They are numbers of the form. Maybe you can tell me. Yeah, those are examples, right? Yeah, good, yeah. So, I have written a few without thinking much. 1 by 2 is an example, 2 by 3 is an example, 2 by 7, 41 by 6, 175 by 60. So, what is the property of these numbers? There is a line here, and there is an up, and there is a bottom. And up you put some number, which is a natural number, and bottom you put another natural number or the same natural number, one more natural number. You could have put a negative number also, but we are all about, counting and distance and all, so we are in the positive framework. Okay. So these are rational numbers. So I've said positive rational numbers because you could have taken minus 1 by 2, etc. also. Doesn't matter. Okay. So this is all that I need. The notion of a right angle triangle, and you already know how to compute its area, which was easy. And what are rational numbers? That's all that I need to know to introduce the problem of today's talk. So fractions where both up and bottom are natural numbers, and each natural number is a rational number, right? Why is that? Because if you give me 10, I will think of 10 as 10 divided by 1. So there is an up and bottom. Bottom is 1, so obviously it's 10 itself. So now I'm going to say a natural number. I'm going to define what a congruent number is. Okay? And then the problem is about studying these congruent numbers. So what is a congruent number? So please pay attention. Many of you might not have seen this before. A natural number n is called congruent if you can find a right triangle. Only thing is a right triangle may have 1.111 whatever root 2 as a side, etc. Non-rational numbers can be there. When we draw a line, we don't know exactly how much its length is. Assume that all the three sides have length rational numbers. Okay, so you are interested only on those triangles, right angled, all whose sides are rational. All I am stressing, underline, rational also I am stressing. See, two things if you make rational also, it's not clear that the third thing will be rational. That may not be rational, though, so I will not count those triangles. So only those triangles where all the three sides are rational numbers. Then you compute the area. Now the area may be something, right? If you can obtain a natural number as the area of such a triangle, call that number congruent. Okay, so it's a definition. So let's see some examples, right? Just to have some feeling for this definition. But before I, state the most obvious example, maybe you can tell me one. At least two students have already, interacted with me. Yeah.
6, 8 and the hypotenuse being 10.
6, 8 and hypotenuse is 10. So is my condition satisfied? All whose sides are rational? Yes, because you said 6, 8 and 10. Is that a right angle triangle?
Yeah, in a right.
Because 6 square is 36, 8 square is 64. If you sum it is 100, which is 10 square. Therefore, it has to be a right angle triangle. So everything is satisfied. So we just need to compute the area. You said 6, 8 and 10. So it is half times 6 times 8. Half times 6 times 8 is 3 times 8 is 24. So what is the answer? 24 is an example of a congruent number, and he is absolutely right. Okay, so 24 is an example of a congruent number. Now the question is, the problem is, which numbers are congruent and which numbers are not? That's the question. And even today, one has not proved exactly how to classify, which numbers are congruent and which numbers are not. Somewhat surprising, no? Such an easy definition, and all basic things other than rational number and area of a triangle, we did not have to know anything else, and the problem remains unsolved as of today. Okay, but of course there are various great achievements, and I will narrate some stories. But some of the basic aspects we will go through like this. So this is the most basic example. You said 6, 8, 10. I have just divided everything by 2. Okay, so 6 by 2 is 3, 8 by 2 is 4, and 10 by 2 is 5. What is the area? Area is 6. 3 into 4 is 12, divided by 2, 6. So 6 is an example of a congruent number. Here is another example. 5, 12 and 13, again you can check. 5 square is 25, 12 square is 144. If you add, it will be 169, which is the square of 13. So that's another example of a right angle triangle with all rational sides. In fact, here it's natural number itself. What is the area? What is the area? 5 into 12 divided by 2, 30. So 30 is an example of a congruent number. It's not so obvious like this. Some of the easiest triangles that you think of, you will not get area as 5. But that one, the definition did not say it has to be something easy from which you get the area, right? It can be in a slightly difficult way also. So this is something that I saw somewhere. I would not have come up with it maybe. But if you take these sides, 40 by 6, 9 by 6, 41 by 6 are allowed, right? They are all rational numbers, right? And you can check, sum of the squares of first two will be the third. Let's assume all that, everything is correct. And then when you compute the area, it is half times 40 by 6 times 9 by 6. It should be 5. I don't think there will be a mistake there. I have not checked it myself, but you can check. Okay, it is area 5. There is by 6 and by 6 and all, you will get 5. Okay, so that means 5 is also a congruent number. And 7 is also a congruent number. You can check later. This should work out and the answer should be 7. So as of now, we have seen 6 is a congruent number, 30 is a congruent number, 24 that he has given me is a congruent number. And 5 and 7 are also congruent numbers, and this is a convincing proof. I mean, if someone has exhibited something, you only have to verify it is true, and therefore these are congruent. Do you agree with this sentence? 6 is so easily congruent, but 5 or 7 not that easily. Is that true in some sense? Yeah, because that is something that you came up with on your own. This is something that I took from somewhere and showed it to you. Even I have not come up with on my own. So in some sense, and this is true, and this gives you the first indication if the total problems remains kind of unsolved, etc. Okay, there is some merit to it, the difficulty of the problem, because see, 5 and 6 are not very far, and one of them being congruent was easy, and the other being congruent was not so easy, not that difficult, but not so easy. So there is there is no easy way to generate congruent numbers, etc. Anyway, to save time and to keep going, I will do what many people do. I'll just search and just give you some first few congruent numbers. Just to we are still in the stage of developing more and more feel for the topic. So I have just copy pasted. By the way, before coming to that, let me advertise this. There is this nice website called the Online Encyclopedia of Integer Sequences, founded in 1964, and all kinds of, there are all kinds of numbers and interesting properties and any property that anyone has thought of, and if you have generated the sequence, this website has the first, 100, 150 of those. So if one wants to do experiments with numbers, there's a lot of things which you don't have to do, you can go and check. And what I have done is, I think they have till 120 or something. I just copy pasted the numbers below 100. So let's just stare at it. 5, 6 and 7 we have already seen are congruent. Then 13, 14, etc. up to 100, there are many, right? So many congruent numbers are there below 100 itself. It's not such a rare thing or whatever. But what are the other things that you notice just from this list? Trust this list. It is from a trustable place. What is the first thing that, many of you may notice many different things. Okay, red is by color. Yeah, red ants and black ants, you see. There are red ants and black ants. And then, anything else you notice? Red I will come to much later if there is time. Otherwise, it's not a topic for today. That's a very nice observation. 5, 6, 7 consecutively has come. Then something else consecutively has come. Very good. It's amazing. Okay, I have given this lecture in many places to advanced maths people. Nobody has observed this. It's coming to the crux of the problem in some sense. Very good observation. Anything else? This observation, all of you heard what he said? Numbers are coming, 5, 6, 7 came together, and then you said 13, 14, 15, and okay, not every continuous thing I may not want to count, but here I can count. I think you are right, sir. So all these three things coming together, we will see, when we state the problem, that is going to the crux of the problem. Yeah. Very good. Red numbers are not consecutive. Much more than that, the funners, they are supposedly very, very rare. Okay, I will say that in few more words later, but I am very, very delighted that you made that observation. Not only that it's consecutive, not only that it's rare, in some sense it's surprising, when we come to it a bit later, that out of 100 you actually got 3 red numbers. That itself is surprising. One is expecting less than that in some sense, but it so happened that 3 are there. Okay, so beautiful. And someone here was saying something? In everything that is true, that may not be true always, but sometimes it's true, but not always, maybe. That also may be an aberration. That's why I said, let's take 3, 5 can come, but that's not guaranteed. But this coming 3 together, going to, something very central, which we will see later. Yeah, one more, yeah. 3, 5, 7, 9.
5, 6, 7 is 3. And then 13, 14.
Yeah, that's what I was saying. When 3 things are coming together, and someone else observes at some point 5 things came together, but this 3 coming together is something fundamental. Yeah, which is what you also are saying. Yeah.
So after 7 there's like 6 numbers gap, and then there's 13. After 15 there's 5 numbers gap. After 24 there's 4 numbers gap. After 31 there are 3 numbers, and after 39 there are 2 numbers to 41. Again after 47 there are 5 numbers. After 56 4 numbers.
Okay. So that's very impressive that you observed so many patterns in this. But how much of that will be part of general thing, I am not so sure as of now. Okay, but it's a very nice observation. So good. So one thing that we learned, I mean I am learning with you right now is maths is also an experimental science. This is not what we are taught, right? It's all about pen and paper and deep thinking. But we took something from some trusted source, and already many people have observed many things, and we are actually doing experiments, right? It's all observing something and inferring something out of it. Let's move on. So this is good. Here is one observation which I didn't have to say, because your first example was 24 and then I made the smaller example 6 out of it. What is the difference in terms of multiplication between 6 and 24? 4. And what was the difference between this triangle that I wrote and the triangle that you said? Minus 3, 4, 5. His is 6, 8, 10. What is the difference? Sides? Multiply by 2. All the sides. So that is exactly my next slide, which you anticipated. Okay. So here you have the 3, 4, 5 triangle. What I have done is I double the length, double the height, and then automatically hypotenuse gets doubled, and it became 6, 8, and 10. And then you got the area to be 24, and my area was 6. And is there anything surprising there? No, because this you can check easily. The larger triangle, when I doubled each side, the area gets multiplied by 4, which is the square of 2. And that's obvious, right? Because if I multiply this by, let us say, by 5, 15, and if I multiply this 4 by 5, 20, what will be the area gets multiplied by? 25, because area was this into that. So if I multiply this by 5 and that by 5, then 5 into 5 is getting multiplied. So area will get multiplied by a square, which means in order to study congruent numbers, we may as well focus on what have I underlined? Square free numbers. So those of you who have not seen the word square free, what is the meaning of square free? Any number which does not contain a proper square, you remove all the squares. So is 24 square free? No, it contains a square 4. If you remove 4, is 6 square free? Yes, because it does not contain a square. Is 9 square free? No, that itself is a square. What about 9 into 2, 18, is it square free? No, because it contains 9. So if squares are there, you remove, you will get a square free number. One can easily pay attention only to those, because if a number is, which also you could have observed from this previous thing, whenever a number is there, 5 is there, therefore 4 times 5, 20 is also there. 20 is also there, and then 9 times 5, 45 is also there. Square will automatically come, because it's just multiplying this length by something. Good. Okay, so here is something which we got some hunch of, that in the first slide itself, that I said, right, 5 was not so obvious, 6 was obvious. And that is really true. Certain numbers may be congruent. For example, you will not think of as 157 as such a complicated huge number, right? After all, it's only 3 digits. But it is true that 157 is a congruent number. But if somebody asks you to exhibit a right angle triangle, all whose sides are rational, and then the area is 157, there may be many answers. In fact, whenever there is one answer, there are infinitely many answers, which is also not at all obvious, but that I can try to explain this time in this lecture. But the smallest right triangle with area 157, these are the sides. I can't even read it out. Okay. The smallest right angle triangle that one can come up with, all the sides are rational, and the area is 157 is what you see there. And this was discovered by a very famous mathematician called Don Sagier, and this particular one was discovered in 1981. Okay, but at least it it fit into my slide, right? The next one, did you already read? Somewhere I can't read from this distance. Yeah, the number 1063, again, not such a big number, 1063 is within our imagination, and that's also a congruent number. But the right angle triangle that will give you that area with all sides rational has the shortest side A by B, shortest side which has the up 104 digits, and the denominator has 103 digits. So it won't even, how many digits are there here? Much less than 100. So 100 digits will be, much more. So this tells you that, and that was discovered by Noam Elkies in 1982. The problem was from 1000 years ago, and now we are talking about, like 40 years ago, right? So the problem has some inherent difficulties. It is one thing to know that the problem has inherent difficulties. It is another thing to, please let me know when 7 minutes are remaining, let's say, so that, I will do some justice to the remaining slides. But on the other hand, I don't want to rush. When people interact, it's nice to go slow. So what I was saying was, yeah, it is one thing to know that the problem, to get a feel that problems have some inherent difficulties, which I think we have already got from those examples and these huge digits and all that. It's another thing, how to have a systematic approach to attack these problems. Okay, so I will give a glimpse of that also, and that will be the talk. Yeah. Good question. Who asked this? Yeah, so as of now, I have only described the problem as, let us see which numbers are congruent and which numbers are not. But then these days, when people say congruent number problem, it is one particular statement, which also some people have observed here, including you, but I will state it precisely. Yeah. So from our first few lists, this is another thing which nobody told me. I'm sure many of you observed. 1, 2, 3, 4 were missing. No, the first 4 numbers were not congruent. And they are not, as of now, only because it's not there in my table, right? Proving these required new insights. So that the number 1, you cannot get as the area of a right angle triangle, all whose sides are rational numbers. See, to say that something is a congruent number, however difficult it is, let us say 1063. Finally, somebody could actually give you one example, right? Take this side, take that side, and someone has given a side, you can take your time and compute and say, okay, this is. How do you say something is not congruent? See, you have tried with 5 triangles, you have tried with 10 triangles, all of you together have tried with, 10 million triangles, you have not got that number as the area. Does that show that number is not congruent? No. Other person sitting, they may come up with a 10 million and first triangle where that might happen. No. So showing this is one thing in mathematics. To say that something is true, many times, one may not be able to exhibit, but at least there's a hope. Sometimes something you can exhibit and show. But to say something is not, you will have to rule out all the possible exhibits that you can think of. And that's not a finite thing to do. So there should be other ideas, other insights, and this was done. So do you agree from whatever we have discussed, if one is not, suppose, I proved to you, Fermat did that job for me. If someone proves that 1 is not a congruent number, do you agree that 64 is not a congruent number? 100 is not a congruent number? Any square is not a congruent number? Because we said this once. If a number is congruent, if and only if any square multiple of that is congruent. So if 1 is not congruent, then no square is congruent. It follows. Okay. So 1 and therefore any square is not a congruent number. Fermat proved this. You have heard the name Fermat? Pierre de Fermat. He was certainly mathematics was his hobby. Maybe he was an advocate or something, lawyer or something. And this was many years ago. I have the exact dates and the picture in the next slide. And by the same methods, one can show that 2 is also not congruent. So among 1, 2, 3, 4, 1 is not, therefore 4 is not, because it's a square multiple of 1. 2 is not, again Fermat's method will yield the result. 3 is not was much later. Okay, I will have a historical slide. The proof is very beautiful and in fact can be described in all detail, because it was about getting one insight, which Fermat got. Now that he has got the insight, for me to, go through that insight and explain is not all that difficult. Okay? But still I won't attempt it here because, it's better that it's in a smaller room. Okay, this is too big a room and, it might take some time, though it's easy. Sometimes easy things also take time to, go step by step. For that reason I skip, but typically in a lecture like this, I do give the proof. And the proof is just one paragraph in Wikipedia. So those of you who are interested, one can see the proof. It's not difficult at all. You only need high school mathematics. But there is an ingenious idea. That idea, maybe I will use the word here. That idea, this is a quote from the Wikipedia article on what is called the Fermat's right triangle theorem. And it follows from that. He does not talk about congruent numbers, but it easily follows from that. The thing that I underlined here is, what did I underline? Proof by infinite descent. So that's an entire, philosophy of proving things in mathematics. I cannot say this is the first time it came because people go back and see in Euclid also this thing was there. But this is what made, that particular approach famous. And this ingenious idea was required. And then, showing it to you, it won't be very difficult. And I leave those who are interested to, have a look at Wikipedia or some other source. It's just one paragraph. Okay. So let's move on. This is Pierre de Fermat. By the way, Fermat is very famous for something else which many of you know. Yeah, so that also got mentioned in that wiki code that I said, right? Fermat's last theorem. So this got proved when I was in school, college, sometime like that. So not that long ago. And that became famous because he claimed that, Fermat's marginal nodes. It became famous because I think you know. So
Proved by Andrew Weiss in 1990.
Excellent, yeah. And the story, was open for some 400 years. He claimed that, here is a beautiful result. Let me not get into that. And I have a wonderful proof. But the margin of my note is too small to contain that proof. And then that proof was never written. And people tried and tried. All kinds of things came. It took 400 years and much more advanced mathematics. And solved only in 1995 or sometime, as he said. So most people believe, there was no proof. Okay, maybe he thought he had a proof. Okay, whereas this particular one, and somewhere it's written, he actually had a proof, which his son actually got it from some notes and published. Let's move on. So this is Fermat. That 3 is not congruent already requires much more work, and this was done by an Italian mathematician for the first time, Angelo Genocchi, I think, 1817 to 1889. So sometime in between he did that. So that's already much after Fermat, no? This is 1600s, that is 1800, 200 years later. That 3 is not congruent. Actually, Genocchi did a bit more. In fact, he did this particular sequence. What do you observe about this sequence? 3 plus what is 11? 8, 11 plus 8 is 19, 19 plus 8 is 5 minutes? 6 minutes. So in this sequence, if you take any prime number, that is not congruent also he could prove. Okay. So now let me, in the remaining time, let me say, where the advanced maths coming in and, how progress is made. So the problem gets connected to current research in mathematics via 2 words, okay, many words, but 2 key things. One is called elliptic curves, whatever it means, it's called elliptic curves. And the other is called modular forms. Elliptic curves, I have 1 or 2 slides, just to give you some feeling for it. Modular forms, I don't have any slide. I deleted the slide the last moment, but it's not correct not to mention Srinivasa Ramanujan. Modular forms is the area where one of the biggest names is that of Srinivasa Ramanujan. Very intimately connected to this problem, but due to technicalities and lack of time, I won't get into modular forms. But elliptic curve, let me quickly say something. These are, forget all the equations and all that, but it is a curve where, there are polynomials in x and y and the highest degree is 3. So this is what is called a cubic curve, cube 3, okay? And a typical curve will look like this. But this curve, this kind of cubic curves are very, very different from any other curve in degree 5 or degree 10 or degree 1 million or degree 1 that you can think of. For the reason that it has an algebraic structure. Those who know the word in maths is what is called a group. Points there you can take and you can produce a third point exactly the same way, you take 1 and 2 and produce 3. 1 plus 2 is 3. And given 1, you have a negative 1. And given 1 and negative 1, you can add and get 0. There are natural properties of integers. All those can be done with points on this curve in a very precise way, which I have put there, but let me not get into that. And then what happens is, so here is one particular cubic curve, which is called the congruent number cubic curve. And the problem of congruent numbers can be translated into this particular cubic curve in a very precise way. If there is a right angle triangle, which will give you the area as that particular number, let us say n, you just have to plug n there and consider this curve and then ask whether this curve has a point on it. What is a point on a curve? It is x comma y. And when you plug in, that equation will be satisfied. So if there is a point on this curve, x comma y, where both x and y are rational numbers, that is precisely equal to n being a congruent number. And this is also very easy. In fact, there is a slide later which actually shows you how to do it. Just mechanical manipulation. But with that one mechanical manipulation, what one has achieved is, you have transferred the problem of congruent numbers to a rich theory of elliptic curves, where there are all kinds of advanced methods to do. So the problem gets transferred to the theory of elliptic curves. And just to show you how powerful abstractizing something and putting in a theory is, to show that one number is congruent, you had to produce one triangle where the area became that. Now, is that the only way you will get, is there another triangle which would have given you the same area? Maybe or maybe not would be your answer. But if you put it into this theory, it's kind of obvious that if one triangle does the job, there are infinitely many triangles which will do the job. It's not difficult. You only have to put this into theory and see from the perspective of theory. Just to illustrate, underline the point that taking a problem and putting it in the correct perspective, many things come for free. Many things which were far from obvious when you stare at it straight away. So I will stop by, telling one particular thing. There is a very, very celebrated conjecture called the Birch-Swinnerton-Dyer conjecture. Birch is one name and Swinnerton-Dyer is one name. Okay. If I ask for patterns, maybe some of you would have said there are 3 names because there are 2 hyphens. Okay. So there is a very famous conjecture and it is still unsolved. And the problem gets transferred to knowing the truth of this conjecture, not for any elliptic curve, but for that particular elliptic curve, which I wrote down in the last slide, y square equal to x cube minus n square x. And this conjecture is about, how to determine whether there are rational points on an elliptic curve. And if there is rational point on that particular elliptic curve, the corresponding number is congruent, otherwise it's not. It's both ways. And now, let me end by, this is Birch and Swinnerton-Dyer, the patterns that the audience has observed, why it was to the crux of the problem. A consequence of knowing the truth of that conjecture would be any number of the form a multiple of 8 plus 5, a multiple of 8 plus 6, a multiple of 8 plus 7. These are certainly congruent. Not a single exception. This is what exactly you observed earlier when you said 5, 6, 7 come together, then 3 numbers come together, then 3 numbers come together. You had anticipated, what is coming out of this such a famous conjecture. So they are congruent is a conjecture, not a theorem. Why? Because Birch-Swinnerton-Dyer conjecture is not proved. Okay? And therefore, this is what is expected. Can you say the other way that 8k plus 1, 8k plus 2, 8k plus 3 are not congruent? That is not true because I had those red numbers. The red numbers were precisely the numbers in that chart which were not 8k plus 5 or 8k plus 6 or 8k plus 7. One number was 34. That is modulo 8 is 30 plus 4. No, 4 into 8, 32 plus 2. So it is 2 mod 8. It is of the form 8k plus 2. Another number was 41 in red. So that is 8k plus 1, 5 into 8 plus 1. So those numbers are in general not, but once in a while it can be. But when it happens, it is very, very, very rare. And as this very small boy told me, it is supposedly very, very rare. Okay? And again, that can be seen from this general theory. And this is what now one goes by to answer your question. When one says congruent number problem, it is to assert that 8k plus 5, 8k plus 6, 8k plus 7 are indeed congruent. Prove it. Of course, it's true. I cannot say of course it is true because there's no proof. But, it is expected to be true. But then prove it as a congruent number problem. There are a lot of advances which I have put in my last slide here. And in fact, this particular one is very recent, 2014. One has made, great progress towards that problem, but far from being solved. So to summarize, here is one example of a problem whose statement was easy. I hope everybody appreciated the definition and the problem that is formulated. But the last slide tells you that there is tremendous progress, including in recent years, but we are far from actually fully solving the problem. And my last sentence is number theory is full of such problems where statement is easy, but very, very difficult to reach. Yeah, stop here.
Thank you very much. This was a very exciting talk, especially for a Chennai audience, the land of Ramanujan. Yeah. So, of course, there has been a lot of interaction during this talk, but there are a few questions which have come in. The first question, actually, I'm not sure whether it was already answered later in the talk because it came earlier. Given the sequence of numbers from the online encyclopedia, is it proven that the missing numbers there are indeed not congruent numbers?
So the quick answer, in that particular chart, these are small numbers, so, using computer, otherwise people would have verified. Numbers which are not there below 100, they are certainly not. But how to get a general strategy for bigger numbers is tough.
So for up to 100, we know exactly.
Up to 100, of course.
Maybe
not
using.
Not just up to 100, I'll just flash, so with computers, many things can be done. So how do I go to the. So, here I stop my talk, but. So the following slides, which are not part of such a talk. See, all kinds of, up to 200, I don't know, such a big number, 2 crore, 20 crore, whatever. Computers can do and tell you many things. Yeah. So.
Okay.
Yeah.
Okay. Nice to know that. The next question is from Shubham. He asks, the definition of congruent numbers itself is related to the right angle triangles. And is it possible to consider other kinds of triangles and come up with some interesting definitions or sequences?
So such a question, obviously one cannot or should not answer no, right? Who knows, maybe tomorrow somebody can. But there is no, this kind of a famous problem with a non-right angle triangle.
Okay. Okay, I think that's all the questions that are here for now. I'd just like to remind everybody that there will also be a question answer session at the end of all the 4 talks, where all the 4 speakers will be here and you can pose your questions again to them. So continue sending them to these handles which are mentioned here.
Thank you.
Join me once again in thanking Anand.